Welcome to the Sleepy Science channel. Like, subscribe, and write where you are watching from. Now gently settle in and allow your thoughts to drift as we begin a calm journey through one of the most powerful forces known in the universe, nuclear energy, or so immense that even a small amount of matter can release energy comparable to the brightness of a small star. And yet this same force behaves very differently depending on where it is released, whether on Earth, on distant planets, or in the silent emptiness of space. A nuclear explosion begins deep within the structure of atoms, where the nucleus, tightly bound by powerful forces, can be split apart or fused together, releasing energy that has been stored since the formation of matter itself. In fission reactions, heavy atoms, like uranium or plutonium, are split into smaller pieces, releasing heat, radiation, and fast-moving particles, while in fusion reactions, lighter atoms, such as hydrogen isotopes, combine under extreme conditions, producing even greater energy. Similar to the processes that power stars, in both cases the result is a sudden and overwhelming release of energy that expands outward in all directions. On Earth, this energy forms a bright fireball, followed by a powerful shockwave that travels through the air, pushing and compressing everything in its path. But this familiar image depends heavily on the presence of an atmosphere, because air carries the force of the explosion. Without air, the behavior changes completely. And this is where our journey begins to stretch beyond Earth, into environments where the rules we are used to no longer apply in the same way. In space, where there is almost complete vacuum, a nuclear explosion would not produce a traditional blast wave. There would be no roaring pressure front, no rolling cloud. Instead, the energy would move outward mostly as radiation and extremely fast particles. The fireball would still form briefly, glowing intensely as matter is heated to extreme temperatures. But it would expand silently, fading into darkness without resistance, as there is nothing to push against, nothing to carry sound, nothing to shape the explosion into the forms we recognize. This difference is essential, because when we begin to imagine nuclear explosions on other planets, we must consider their unique environments. Some worlds have thick, crushing atmospheres. Others have almost none. Some have solid rocky surfaces, while others are made of deep layers of gas. And each of these conditions changes how energy moves, how heat spreads, and how matter responds to the sudden release of power. Gravity also plays a quiet but important role. Stronger gravity can pull debris back toward the surface more quickly, shaping the aftermath of an explosion, while weaker gravity allows material to travel farther, sometimes escaping into space entirely. The composition of the surface matters as well. Rock, ice, dust, or liquid all react differently when exposed to extreme heat and pressure, creating different types of craters, clouds, and long-term changes. As we continue, imagine each planet not just as a distant object, but as a unique stage, each with its own rules, its own textures, its own invisible forces guiding the movement of energy. A nuclear explosion is not just a single event. It is a conversation between energy and environment, a moment where the fundamental forces of nature reveal themselves in different ways depending on where they unfold. So as your mind begins to slow and wander, picture the quiet surface of the Moon, the dusty plains of Mars, the thick clouds of Venus, and the deep swirling storms of Jupiter, each waiting in silence, each ready to respond differently to the same burst of energy. And in understanding these differences, we begin to see not just the power of nuclear explosions, but the deeper nature of the worlds themselves, shaped by physics, guided by invisible laws, and endlessly fascinating in their quiet complexity. As the quiet flow of thought continues, imagine that same burst of nuclear energy, identical in its origin, yet placed gently onto different worlds, each with its own invisible rules, its own silent resistance or acceptance. Because an explosion is never only about the energy released, it is always about the environment that receives it, the medium that carries it, the gravity that pulls it, and the surface that absorbs or reflects it. One of the most important conditions is the presence of an atmosphere, because air is not empty, it is a dense sea of particles. And when energy is released into this sea, it pushes outward, compressing the air, forming what we call a shockwave, a moving wall of pressure that carries force across great distances. On Earth, this is what shatters structures and shapes the familiar expanding ring of destruction. But remove the atmosphere, and this mechanism disappears almost entirely, leaving only radiation and fast-moving particles to travel outward in silence. The thickness of an atmosphere changes everything. A thin atmosphere like that of Mars allows only a weak shockwave to form. The energy spreads quickly and loses strength, while a dense atmosphere like that of Venus behaves very differently. There the air is so thick, so heavy, that it resists expansion, trapping heat, compressing the explosion, and potentially amplifying certain effects, making the fireball behave in a slower, more contained way, almost as if the planet itself is holding the energy close for a brief moment before releasing it. Gravity adds another quiet influence, not immediately visible, but always present, guiding the motion of debris and heated material on a low-gravity world like the Moon. Particles thrown upward by an explosion can travel great distances, some even escaping into space entirely, while on a high-gravity world, the same material is quickly pulled back down, falling in arcs, returning to the surface, shaping the aftermath into thicker deposits and more compact structures. Surface composition also plays a subtle but powerful role. A solid rocky surface absorbs and reflects energy differently than loose dust, ice, or liquid. On a rocky planet, the explosion may carve a sharp crater, melting and vaporizing material, while on an icy world, the heat can instantly turn solid ice into expanding steam, creating plumes and fractures. And on a dusty surface, fine particles can be lifted into the air, forming clouds that drift and settle slowly over time. Pressure, often unnoticed, becomes critical in extreme environments. In high-pressure conditions, the expansion of the fireball is resisted. The gases cannot expand freely, and this changes how energy is distributed. Heat may remain concentrated for longer, and the visible structure of the explosion may appear more compressed, more contained, while in low-pressure environments, the opposite happens. Expansion is rapid, uncontrolled. Energy spreads thinly and quickly fades. Temperature of the environment adds yet another layer. In extremely cold regions, materials may be brittle, reacting to sudden heat with cracking and fragmentation, while in extremely hot environments, the surrounding matter may already be near its limits, and additional heat pushes it into new states, altering how it flows, melts, or vaporizes. Even the presence of magnetic fields and radiation belts can influence how the energetic particles from a nuclear explosion move, especially in space or around large planets, where invisible magnetic lines guide charged particles, bending their paths, spreading them in ways that are not immediately visible but deeply important over time. All these conditions, atmosphere, gravity, surface, pressure, temperature, and magnetic influence, combine quietly, shaping each explosion into something unique, even though the source remains the same. And as you let your thoughts drift across these distant worlds, you begin to see that a nuclear explosion is not a fixed event, but a flexible interaction, a moment where energy meets environment, and together they create something entirely dependent on where it happens. Now, imagine placing this same burst of energy onto a silent gray world, with no air at all, a place where shadows are sharp and the sky is always black. The moon awaits quietly, unchanged for billions of years, and soon we will gently explore how such an explosion would unfold there. In complete silence, under a sky that never carries sound. Now let your thoughts drift toward the quiet surface of the moon, a world without wind, without weather, without sound, a place where time moves slowly and marks are preserved for millions of years, where every footprint and every impact remains almost unchanged, resting beneath a black sky filled with distant stars. And here, in this stillness, we imagine the sudden release of nuclear energy. The most defining feature of the moon is its lack of atmosphere. There is no air to carry a shock wave, no medium to transmit sound, no resistance to shape the explosion into the forms we recognize on Earth. And so when a nuclear device detonates on this silent surface, the event unfolds in a way that feels almost unreal. A brief flash of intense light, brighter than anything in the lunar landscape, followed by the rapid expansion of a glowing sphere of plasma. But without the rolling pressure wave that we are used to, without the thunder, without the spreading wall of compressed air, the fireball forms instantly, heating the surrounding material to extreme temperatures. Lunar soil, known as regolith, is composed of fine, dry particles, sharp and loosely packed. And when exposed to such intense energy, it does not behave like solid rock alone. Instead, it vaporizes, melts, and is thrown outward in all directions, creating a spray of glowing debris that rises in graceful arcs, unopposed by air resistance, each particle following a clean, silent path through the vacuum. Because gravity on the moon is much weaker than on Earth, about 1/6 as strong, the debris travels much farther, rising higher, moving in long curved trajectories before slowly falling back to the surface. Some particles may even reach escape velocity and drift away into space, becoming tiny fragments orbiting quietly or disappearing into the vast darkness, while others return, forming a wide blanket of newly disturbed material around the point of explosion. Instead of a mushroom cloud, there is a momentary dome of expanding material, a ghostly shell that grows and fades, not held together by air, not shaped by turbulence, just expanding freely until its energy is spent, and then slowly collapsing back into stillness, leaving behind a crater that tells the story long after the light has vanished. The crater itself would be sharply defined, with edges that remain crisp for long periods, because there is no wind or rain to erode it. The heat of the explosion would melt portions of the surface, creating glassy textures, frozen instantly as the energy dissipates, and the surrounding area would be covered in a layer of fine ejecta, spread outward in a pattern that reflects the symmetry of the blast. Radiation behaves differently here as well. Without an atmosphere to absorb or scatter it, much of the initial radiation would travel directly outward into space, while some would interact with the surface, altering materials at a microscopic level. But there would be no widespread atmospheric contamination, no drifting radioactive clouds, just a localized imprint, quiet and contained. From far away, perhaps from Earth, such an explosion might appear as a brief, bright flash on the lunar surface, visible for a moment, then gone, leaving no sound, no smoke, no lingering sign except for the subtle change etched into the ancient terrain, a new mark among countless old ones, another story added to the long memory of the moon. As you continue to relax into this slow journey, imagine that silent flash fading, the dust settling back into place, the surface returning to stillness as if nothing had happened. And now gently shift your attention to a different world, the red plains of Mars, where a thin atmosphere whispers across the surface, and where the same burst of energy would begin to behave in a slightly more familiar, yet still very different way. Now let your mind drift gently toward the distant red world of Mars, a planet that feels almost familiar, yet quietly different in ways that shape every movement of energy across its surface. A place where a thin atmosphere stretches lightly above vast deserts of dust and stone, where winds move slowly and where the horizon glows with a soft, reddish haze. Unlike the moon, Mars does have an atmosphere, but it is extremely thin, less than 1% of the density of Earth's air, and this changes the nature of a nuclear explosion in subtle but important ways, because now there is at least some medium to carry a shockwave. some material to push against. And so when the explosion occurs, there is a brief formation of a pressure wave, a faint and spreading pulse that travels outward, but it is weak, quickly losing strength as it expands into the thin Martian air. The fireball still forms instantly, a bright sphere of intense heat and light, vaporizing the dusty surface beneath it. But here, unlike on the moon, there is just enough atmosphere to begin shaping the expanding gases, creating a distorted, short-lived cloud, something that hints at the familiar mushroom shape seen on Earth, yet never fully forming, never fully sustained, because the air is simply too thin to hold it together. The Martian surface plays a powerful role in this moment, covered in fine dust that has settled over millions of years. When the explosion releases its energy, this dust is lifted into the air, forming a rapidly expanding cloud that spreads outward across the landscape, glowing faintly as it reflects the light of the fireball, and then slowly drifting as gravity begins to pull it back down. Gravity on Mars is stronger than on the moon, but still weaker than on Earth, and this creates a balanced motion in the debris. Particles rise higher than they would on Earth, but not as freely as on the moon. They arc outward and long. Slow curves, carried slightly by the thin winds, settling over a wide area, leaving behind a layered pattern of disturbed surface material. One of the most fascinating effects comes from the interaction with Martian dust storms, which are known to grow into massive, planet-wide events. If a nuclear explosion were to occur during such a storm, the energy could disturb the already moving dust, adding to its motion, creating complex patterns in the air. But it would not trigger a global reaction. The scale of the planet is too vast, and the energy, while immense, is still localized compared to the size of Mars itself. Heat behaves differently here as well. Without a thick atmosphere to trap it, much of the thermal energy escapes quickly, radiating into space. The fireball cools faster than it would on Earth, and the surrounding area, though intensely heated at first, returns to its cold baseline relatively quickly, leaving behind a surface that shows clear physical change, but limited long-term atmospheric impact. Radiation spreads in a mixed way. Some is absorbed by the thin atmosphere, some escapes into space, and some interacts with the surface, altering the chemistry of the soil, but again, without dense air to carry particles across long distances. The contamination remains relatively localized compared to what would happen on Earth. The crater formed would be softer at the edges compared to the moon, because of the dust, its shape influenced not only by the explosion itself, but by the slow movement of wind over time, gently reshaping its outline, smoothing its sharpness, blending it into the surrounding terrain. If observed from orbit, the explosion would appear as a bright flash followed by a spreading cloud of dust, rising and expanding before slowly fading into the background of the planet, a brief disturbance in a world that otherwise remains quiet and still. And as this red dust settles back into place, as the faint echoes of motion disappear into the thin Martian air, allow your thoughts to drift further inward toward a much harsher world, one where the sun burns intensely overhead, where shadows are sharp and the surface is both frozen and scorched at once. The small and extreme planet of Mercury awaits in silence. Let your thoughts drift closer to the sun, toward the stark and silent world of Mercury, a place of extremes, where daylight burns with intense heat and night falls into deep cold, where the sky remains forever black, and where the surface, marked by countless impacts, rests unchanged for ages, untouched by wind or rain. Mercury, like the moon, has almost no atmosphere, only a very thin exosphere made of scattered atoms, far too sparse to carry a shockwave or sustain any kind of cloud formation. And because of this, a nuclear explosion here would unfold in a way that feels both familiar and starkly minimal. A sudden burst of light, an expanding fireball, and then a quiet fading into darkness. When the explosion occurs, the energy released would instantly heat the surrounding surface to extreme temperatures. The rocky ground, already hardened by constant exposure to solar radiation, would melt and vaporize in an instant, forming a glowing pool of molten material that is thrown outward in all directions, much like on the moon, but under far more intense sunlight, making the initial flash even more blinding to any distant observer. Without air, there is no shockwave, no rolling pressure front, no sound, only the pure expansion of energy and matter into the vacuum. The fireball would grow rapidly, then dissipate just as quickly, its edges not shaped by turbulence, but by the simple physics of expansion in empty space, a smooth and silent sphere of glowing plasma that fades as its energy spreads outward. Gravity on Mercury is stronger than on the moon, but still weaker than on Earth, and this influences how debris moves after the explosion. Fragments of rock and molten droplets are launched into the air, following long curved paths, some traveling great distances before falling back to the surface, while finer particles may rise higher and remain suspended for a brief moment before settling. One unique aspect of Mercury is its extreme temperature contrast. On the side facing the sun, the surface can become incredibly hot, while the shadowed regions remain freezing cold, and this creates an interesting interaction, as the explosion adds intense heat to an already hot environment, potentially causing surrounding materials to behave more fluidly, while in colder regions, the sudden heat may cause rapid expansion and cracking, breaking the surface apart in sharp, brittle fragments. The crater formed by such an explosion would be sharp and well-defined, much like on the moon, but the surrounding material might show more signs of melting and re-solidification, forming smooth, glass-like areas where the surface has briefly liquefied and then cooled again, locked in place under the harsh sunlight. Radiation from the explosion would mostly escape directly into space, with very little being trapped or scattered, because there is no atmosphere to hold it. The effect would be highly localized, leaving behind changes in the surface material, but not spreading far beyond the immediate area. From a distance, perhaps from a spacecraft orbiting the planet, the explosion would appear as a brief, intense flash against the dark and sunlit contrast of Mercury's surface, a momentary disturbance in a world that otherwise remains still and unchanged for millions of years. As the light fades and the surface returns to its quiet state, imagine now a very different world, one wrapped in thick clouds, where pressure is immense and heat is constant, a place where the same explosion would not expand freely, but instead be held, compressed, and shaped by an atmosphere so dense that it changes everything. The mysterious and heavy world of Venus waits beneath its endless clouds. Now let your thoughts drift toward the immense presence of the sun, a sphere of glowing plasma, so vast and powerful that every planet, every orbit, every moment of warmth in our lives depends on its steady energy. And here, the idea of a nuclear explosion becomes something very different, something that almost dissolves in scale before it even begins. At first, imagine the event itself, a nuclear device reaching the outer layers of the sun, entering a region already hotter than any fire we know, where temperatures reach thousands of degrees at the surface and millions deeper within, where matter is not solid or liquid, but plasma, a sea of charged particles moving constantly, guided by powerful magnetic fields. When the device detonates, the reaction still occurs. Atoms release their stored energy in a brief and intense flash. A tiny fireball forms, expanding outward. But here, this fireball is immediately surrounded by an environment that is already far more energetic. The sun is continuously producing energy through nuclear fusion, releasing amounts of energy every second that are billions of times greater than any human-made explosion. Because of this, the explosion does not stand out in the way it would on a planet. It is absorbed almost instantly, its energy blending into the surrounding plasma, becoming indistinguishable from the natural motion and heat of the sun. Like a small ripple dropped into an endless ocean of fire, There is no shockwave in the traditional sense, because the sun is not a solid surface or a stable atmosphere like a planet. Instead, the explosion would create a very small local disturbance, a brief expansion of plasma, a tiny flicker compared to the vast solar activity that is always present. Solar flares and magnetic eruptions already release far more energy naturally. Radiation from the explosion would simply add to the constant stream of radiation already pouring from the sun. Lost within its brightness, unable to create any noticeable increase when viewed from afar, the sun's own light overwhelms everything. Even if many nuclear devices were somehow used together, the scale difference remains overwhelming. The sun's mass and energy output are so immense that human technology cannot meaningfully alter its structure, its reactions, or its long-term behavior. There would be no visible mark left behind, no crater, no lasting disturbance, only a momentary and extremely small fluctuation in a system that is constantly shifting and moving, powered by forces far beyond anything we can create. From Earth, nothing would be seen. No flash, no change in brightness, no effect on sunlight. The sun would continue exactly as before, steady, constant, unchanged. And in this final reflection, there is something calming, a reminder of scale, that even the most powerful things we can build are small compared to the natural processes of the universe, that the sun, quietly burning for billions of years, remains far beyond our ability to influence. As your thoughts settle, imagine that tiny burst of energy dissolving instantly into the vast glow, becoming nothing more than a fleeting whisper in a star that never notices it, and then gently let that image fade into warmth and stillness. Now let your thoughts drift into the dense and veiled world of Venus, a planet hidden beneath thick layers of clouds, where the atmosphere presses down with overwhelming force, where heat never escapes, and where the surface glows with a quiet, relentless intensity far beyond anything felt on Earth. And here, the behavior of a nuclear explosion changes in a profound and almost heavy way. Venus possesses an atmosphere unlike any other rocky planet in the inner solar system, composed mostly of carbon dioxide and nearly 90 times denser than Earth's atmosphere. This immense pressure creates an environment where gases are tightly packed, where movement is slow and resisted, and when a nuclear explosion occurs within such a dense medium, the expansion of energy is no longer free. It is held back, compressed, and forced to interact continuously with the surrounding air. At the moment of detonation, the fireball forms, as always, a sphere of intense heat and light. But instead of expanding rapidly outward, it meets immediate resistance. The thick atmosphere pushes back, slowing the expansion, increasing the pressure within the fireball, and causing it to remain more compact for a longer period of time. This creates an effect where the energy stays concentrated, building and interacting with the surrounding gases in a way that amplifies thermal transfer. A powerful shockwave forms instantly, far stronger than anything on Earth, because there is so much more material to compress. The dense air carries this wave outward with great force, pushing through the heavy atmosphere, but also losing energy more slowly, allowing it to travel farther while maintaining intensity, and this creates a wide zone of pressure effects that extend across the surface. The heat from the explosion does not dissipate quickly. Instead, it is trapped. The thick clouds and dense gases hold the thermal energy, spreading it slowly, allowing the surrounding region to remain heated for longer periods. And this extended heat interaction could cause additional chemical reactions within the atmosphere itself, subtly altering the composition in localized regions. The surface of Venus, already hot enough to melt certain metals, reacts in a different way compared to colder worlds. The ground, composed of volcanic rock, would absorb the intense heat, potentially melting further and flowing slightly. The explosion could create a crater, but its edges might not remain sharp for long, as the high temperatures and pressure could gradually soften and reshape the surrounding material. One of the most fascinating aspects is how the explosion interacts with the thick cloud layers above. The rising hot gases from the fireball would push upward, disturbing the clouds, creating a temporary clearing or distortion, a brief window through which deeper layers might be visible. But this disturbance would slowly close again as the atmosphere settles back into its dense equilibrium. Radiation behaves differently here as well. Much of it is absorbed or scattered by the dense atmosphere, reducing its reach, but increasing its interaction with the air itself, potentially creating glowing effects or ionization within the surrounding gases, adding a subtle, luminous quality to the aftermath. Unlike the silent emptiness of the Moon or Mercury, here the explosion would be accompanied by a deep, continuous pressure movement through the atmosphere. Not something that could be heard in a traditional sense without an observer, but a physical propagation of energy that moves like a slow, powerful wave through a heavy fluid. From above, from orbit, the explosion might appear as a bright, contained flash beneath the clouds, followed by a spreading disturbance in the cloud layers. A subtle ripple in an otherwise uniform blanket, a sign of immense energy briefly interacting with one of the most extreme environments in the solar system. As this dense world slowly absorbs and smooths over the disturbance, returning to its heavy and unchanging state, allow your mind to drift further outward, away from solid ground entirely, toward immense worlds made not of rock, but of deep layers of gas, where there is no surface to stand on, and where energy behaves in ways that feel even more unfamiliar. The vast and swirling realm of Jupiter begins to emerge in the distance. Now let your thoughts drift outward into the vast presence of Jupiter, a world so large that it could hold all other planets within it, a sphere of swirling clouds and deep, layered gases, where there is no solid ground to stand on, only endless descent into thicker and denser atmospheres. And here, the idea of a nuclear explosion becomes something very different, something that dissolves into the planet itself. On Jupiter, there is no surface in the traditional sense. Instead, there are layers of gas that gradually become denser as one moves inward, starting from the upper cloud tops and extending down into regions of immense pressure. And when a nuclear explosion occurs in such an environment, its behavior depends entirely on the depth at which it is released. If the explosion takes place high in the atmosphere, within the visible cloud layers, the fireball forms as always, a sphere of intense heat and light, but immediately it begins to interact with the surrounding gases, hydrogen and helium, pushing outward, compressing the air, forming a shockwave that travels through the thick atmosphere. Yet even here, the scale of Jupiter diminishes the impact. The explosion, though powerful, is small compared to the vastness of the planet. The expanding gases rise and spread, creating a temporary disturbance in the clouds. A bright flash followed by a darker or lighter patch where the cloud structure has been altered. But this change is fleeting. The powerful winds of Jupiter, moving at incredible speeds, begin to stretch and distort the disturbance, blending it back into the surrounding patterns, erasing the mark over time. If the explosion occurs deeper within the atmosphere, the behavior becomes even more unusual. As pressure increases, the expansion of the fireball is resisted more strongly. The gases cannot expand freely, and the energy is absorbed more quickly by the surrounding material. The explosion becomes more contained, its visible effects reduced, its energy distributed into the dense layers around it. In these deeper regions, the heat from the explosion may create rising plumes, columns of hotter gas that slowly move upward due to buoyancy, carrying energy toward higher layers. But this movement is gradual, shaped by the immense pressure and density, far removed from the rapid, dramatic expansions seen on rocky planets. One of the most important aspects is how quickly Jupiter absorbs the energy. The planet's atmosphere is so vast, so massive, that the energy from a single nuclear explosion is relatively small in comparison, it becomes diluted, spread across a large volume, its effects fading as it is carried away by the constant motion of the atmosphere. There is no crater, no lasting mark on a surface, only temporary changes in cloud structure, subtle shifts in color and motion, patterns that appear and then slowly dissolve, leaving no clear trace of the event that caused them. Radiation from the explosion interacts with the thick atmosphere, being absorbed and scattered, contributing to the heating of the surrounding gases. But again, the scale of the planet ensures that these effects remain localized and short-lived. From a great distance, perhaps from a spacecraft observing the planet, the explosion might appear as a brief flash within the clouds, followed by a small disturbance, a ripple in the endless patterns of Jupiter's atmosphere, quickly stretched and carried away by powerful winds, disappearing into the complexity of the planet's motion. As this immense world quietly absorbs the energy, returning to its constant state of swirling movement, let your mind drift further outward to another giant, more distant and colder, yet still composed of deep layers of gas, where the same event would unfold with subtle differences shaped by lower temperatures and different internal structures. The ringed beauty of Saturn awaits in the quiet darkness. Now allow your thoughts to drift gently toward the elegant and distant world of Saturn, a planet wrapped in delicate rings and layered in soft golden clouds. Where the atmosphere feels calmer than Jupiter's violent storms, yet still vast and deep beyond imagination, a place where energy does not strike a surface, but instead dissolves into layers of gas that stretch endlessly inward. Like Jupiter, Saturn has no solid ground where an explosion can leave a crater. Instead, there are shifting levels of pressure and density, and when a nuclear explosion occurs within this environment, it becomes part of the atmosphere itself, a temporary disturbance rather than a permanent mark. If the detonation happens high within the cloud tops, the fireball forms briefly, glowing intensely against the soft tones of Saturn's atmosphere, pushing outward and compressing the surrounding gases, forming a shockwave that travels through the air. Yet compared to Earth, this shockwave feels smoother, less abrupt, because the atmosphere, while thick, is less turbulent than Jupiter's upper layers, allowing the energy to spread in a more gentle and flowing way. The clouds respond by shifting and opening, forming a circular disturbance, a bright or dark patch that expands outward. But Saturn's powerful winds begin their quiet work almost immediately, stretching the shape, blending it into the surrounding bands, softening its edges until it becomes just another subtle variation in the planet's endless patterns. Deeper within the atmosphere, where pressure increases, the explosion behaves more like a compressed pulse. The surrounding gas resists expansion, absorbing the energy more efficiently. The fireball cannot grow freely, and so its energy is transferred into heat and motion within the dense layers, creating rising currents that move slowly upward over time. Saturn is colder than Jupiter, and this lower temperature influences how the gases react. The heat from the explosion creates stronger local contrasts, warmer regions rising through cooler surroundings, forming plumes that drift upward. But these movements are gradual, almost graceful, shaped by the immense scale of the planet and the steady flow of its atmosphere. There is no sound as we understand it, no explosive roar echoing through space, only the physical propagation of pressure through gas. A silent movement that would only be felt, not heard. If one could somehow exist within those layers, radiation is absorbed and scattered through the atmosphere, contributing to the local heating. But like on Jupiter, the sheer size of the planet ensures that the effects remain small in comparison to the whole. The energy disperses, fades, and becomes part of the planet's ongoing motion. From orbit, the explosion would appear as a brief flash beneath the cloud layers, followed by a spreading disturbance, subtle and short-lived, slowly blending into the surrounding atmosphere, leaving no lasting trace, no scar, no permanent change, only a momentary shift in a world that is constantly moving. Even Saturn's famous rings, far above the main atmosphere, would remain largely unaffected, too distant and too vast to be influenced by a single localized event, continuing their slow orbit untouched by the brief release of energy below. As this gentle disturbance fades into the calm flow of Saturn's clouds, let your thoughts drift even farther outward into colder and darker regions of the solar system, where the giants become more distant, their atmospheres deeper and more mysterious, where pressure and cold shape energy in new ways, and where the same explosion would sink quietly into layers of blue and green. The distant worlds of Uranus and Neptune begin to emerge in the quiet expanse. Now let your thoughts drift farther into the dark and quiet reaches of the outer solar system, toward the distant blue worlds of Uranus and Neptune, where sunlight is faint, where temperatures fall to extreme lows, and where the atmospheres are not only vast, but layered with substances that behave differently than the gases of Jupiter and Saturn, creating environments where a nuclear explosion becomes even more muted, more absorbed, more deeply hidden within the planet itself. These worlds are often called ice giants, not because they are made of solid ice on the outside, but because their interiors contain large amounts of water, ammonia, and methane in dense, fluid-like states, mixed with hydrogen and helium, forming thick envelopes that extend deep below the visible clouds. And when energy is released into such an environment, it does not spread freely. It sinks, it mixes, it becomes part of a slow and complex system. If a nuclear explosion occurs in the upper atmosphere of these planets, the fireball appears briefly, a small burst of light against a dim and distant sky. But the surrounding gases quickly absorb the energy. The shockwave forms but weakens rapidly as it moves through the thick yet cold atmosphere, and the visible disturbance is small compared to the immense scale of the planet. The cold temperature plays a quiet role. The contrast between the heat of the explosion and the surrounding environment is extreme, causing local expansion, but also rapid cooling. As energy is transferred into the surrounding gases, which are efficient at absorbing and redistributing heat, the fireball fades quickly, leaving behind a temporary disturbance that begins to blend into the background. Deeper within the atmosphere, where pressure increases significantly, the behavior becomes even more subdued. The explosion cannot expand freely. It is compressed, its energy distributed into the dense layers, creating slow-moving currents rather than dramatic outward motion. The energy becomes part of the planet's internal flow, contributing to subtle movements that may take long periods to fully dissipate. On Neptune, where winds are among the fastest in the solar system, any visible disturbance would be stretched and carried away quickly, the atmosphere constantly reshaping itself, erasing the signs of the explosion, blending them into the deep blue patterns that define the planet's appearance. On Uranus, where the atmosphere appears calmer and more uniform, the disturbance might linger slightly longer, but even here, the immense scale ensures that the energy remains a small and localized event, fading into the vastness of the planet's layers. There is no surface to scar, no crater to form, only a brief interaction between energy and atmosphere, a momentary imbalance that is slowly corrected by the natural motion of the planet, leaving behind no clear trace, no lasting mark. Radiation is absorbed and scattered within the thick atmosphere, contributing to localized heating, but quickly becoming part of the planet's overall energy balance, spreading outward in ways that are not immediately visible, but deeply integrated into the system. From a distant observer, the explosion might appear as a faint flash, barely noticeable against the dim light of the outer solar system, followed by a subtle change in cloud structure, a ripple that is quickly lost in the slow and steady motion of these cold giants. As this quiet absorption of energy fades into the deep stillness of these distant worlds, allow your thoughts to move inward again, toward smaller bodies, worlds of ice and rock, where the surface is solid but fragile, where beneath frozen crusts there may be hidden oceans, and where a nuclear explosion could break through layers, releasing plumes into space, The icy moons such as Europa and Enceladus begin to take shape in the cold and silent dark. Let your thoughts settle softly upon the pale, frozen surfaces of Europa and Enceladus, distant moons wrapped in ice, where silence stretches endlessly and the ground beneath appears still and solid, yet hides something deeper, vast oceans concealed beneath thick crusts, quietly moving in darkness, untouched by sunlight. These icy worlds are unlike rocky planets. Their surfaces are not rigid stone but frozen shells, layered and fractured, marked by long cracks and ridges formed over immense spans of time. And when a nuclear explosion occurs here, the interaction between heat and ice creates effects that feel almost alive, as if the surface itself briefly awakens. At the moment of detonation, the fireball forms, as always, an intense sphere of light and heat. But here, the surrounding material responds instantly. The ice does not simply melt. It undergoes rapid phase change, solid turning to liquid and then to vapor in an instant, creating a violent expansion of steam that pushes outward with force, even in the absence of a thick atmosphere. This rapid conversion produces a plume, a rising column of vapor and ice particles that bursts upward from the surface, carrying fragments high above the moon, especially on low-gravity bodies like Enceladus, where material can travel great distances, some escaping entirely into space, forming temporary clouds that drift slowly before dispersing. On Europa, where the ice crust is believed to be thicker, the explosion may not fully penetrate to the ocean below unless it is extremely powerful, but it can fracture the surface, creating deep cracks that extend downward, releasing trapped gases or pockets of subsurface material, adding complexity to the plume that rises above. On Enceladus, where the ice is thinner in certain regions and natural geysers already exist, the explosion could enhance these natural processes, amplifying the release of material, creating a brighter and more energetic plume that spreads outward, glowing faintly in reflected light as it expands into space. The absence of a dense atmosphere means there is no traditional shockwave, but the rapid expansion of vapor itself acts as a force, pushing material outward, shaping the environment in a localized but dramatic way, forming a crater that is softer at the edges, mixed with melted and refrozen ice, creating textures that differ from the sharp rock craters seen on the moon. As the plume rises, it begins to cool quickly, the vapor condensing into fine particles that drift and fall back slowly, coating the surface in a fresh layer of frost, a quiet snowfall following a brief moment of intense energy, restoring a sense of calm to the landscape. Radiation from the explosion spreads outward, much of it escaping into space, some interacting with the ice, altering its structure at a microscopic level. But again, the effects remain mostly localized, contained within the immediate region. From a distant perspective, the explosion would appear as a bright flash followed by a graceful plume rising into the darkness, a temporary fountain of light and particles, slowly fading as gravity gently pulls everything back toward the surface. As the frozen surface settles, the cracks remain, the new layers of ice form, and the moon returns to its quiet state, holding within it the memory of that brief disturbance. And now, as your thoughts continue to drift, imagine a world that is not frozen or calm, but restless and active, where volcanic forces constantly reshape the surface, where heat rises from within, and where an explosion would meet fire with fire. The turbulent moon of Io begins to glow in the distance. Now let your thoughts drift toward the vivid and ever-changing world of Io, a place unlike any other in the solar system, where the ground itself is alive with motion, where volcanoes erupt continuously, sending plumes of sulfur and molten material high above the surface, and where the landscape is painted in shades of yellow, orange, and deep red, shaped by constant internal heat. Io exists in a delicate balance of forces, pulled and stretched by the immense gravity of Jupiter. This tidal interaction generates internal heat, keeping the moon geologically active. And when a nuclear explosion occurs in such an environment, it does not arrive in a quiet or stable place. Instead, it becomes part of an already dynamic and energetic system. At the moment of detonation, the fireball forms. But here the surrounding material is already hot in many regions, molten or semi-molten. And this changes how the energy is absorbed and distributed. The explosion adds to the existing heat, intensifying local conditions, causing molten rock to splash and spread, mixing with the expanding gases of the blast. Io has only a very thin atmosphere, composed mainly of sulfur dioxide. So like the moon and Mercury, there is no strong shock wave, no sustained pressure front, but the material on the surface itself responds violently. Molten pools can be disrupted, sending streams of lava outward, while solid crusts may fracture and collapse, revealing deeper layers of heat. One of the most fascinating possibilities is the interaction with existing volcanic systems. If an explosion occurs near an active vent, it could disturb the flow of magma beneath the surface, altering pressure conditions, potentially triggering or enhancing an eruption. Not in a dramatic chain reaction across the entire moon, but in a localized and complex way where natural forces and artificial energy briefly combine. The debris from the explosion, mixed with volcanic material, rises into the thin atmosphere, forming plumes that are shaped more by the initial force of the event than by air resistance. These plumes may reach great heights due to Io's relatively low gravity, spreading outward before slowly falling back, coating the surface in fresh layers of sulfur and rock. The colors of the surface may change subtly in the affected region. The intense heat can alter chemical compositions, creating darker or lighter patches, adding new patterns to a landscape that is already rich with variation. Radiation spreads outward, much of it escaping into space, but some interacting with the thin atmosphere and surface materials, contributing to localized changes, yet again remaining limited in scope compared to the scale of the moon. From a distance, the explosion might appear as a bright flash, followed by an unusually large or irregular plume, blending into the many natural eruptions that already occur on Io, making it difficult to distinguish from the moon's constant activity without careful observation. As the energy settles, the surface continues its restless motion. Lava flows resume, vents continue to release material, and the explosion becomes just another moment in the ongoing story of a world that never truly rests. And now, as your thoughts gently move away from this fiery landscape, imagine a place where there is no surface at all, no ground, no atmosphere, only the vast emptiness between worlds, where energy has nothing to push against, nothing to shape it, and where a nuclear explosion becomes something purely radiant, silent, and fleeting. The open expanse of space begins to surround you. Now let your thoughts drift away from all worlds, away from surfaces, away from atmospheres, into the vast emptiness between planets, into open space itself, a place where there is almost nothing. No air, no pressure, no resistance, only scattered particles and distant light. And here, the idea of a nuclear explosion transforms into something entirely different, something quieter, more abstract, and yet still deeply powerful. In open space, a nuclear explosion has no atmosphere to interact with, no medium to carry a shockwave, and this changes everything about how the energy behaves. Because what we often imagine as an explosion, the expanding blast, the roaring force, depends on pushing against something. And in space, there is nothing to push, nothing to compress, nothing to carry that familiar wave of destruction. At the moment of detonation, the core reaction still occurs exactly the same. Atoms split or fuse, releasing immense energy in a fraction of a second, forming an intensely hot and bright fireball. But this fireball is not shaped by air. It is not slowed by pressure. It expands freely in all directions, a perfect sphere of glowing plasma that grows rapidly and silently into the vacuum. Because there is no resistance, The expansion happens very quickly. The energy spreads out over a larger volume in a shorter time, and this causes the fireball to cool faster than it would on a planet with an atmosphere. Its brightness fades quickly, transitioning from an intense flash to a dim glow, and then disappearing into the darkness. Instead of a shockwave, most of the energy is carried away as radiation. Gamma rays, X-rays, and streams of fast-moving particles. These travel outward at incredible speeds, passing through space without being slowed, continuing until they encounter something, a spacecraft, a planet, or simply dispersing into the vast distances between stars. One of the most striking aspects is the silence, not just the absence of sound, but the absence of any medium to even create sound. The explosion does not roar, it does not echo, it simply happens. A sudden release of energy followed by a rapid fading. A brief event in an otherwise unchanging void. If the explosion occurs near an object, such as a spacecraft or a small body, the radiation becomes the primary source of impact, damaging electronics, heating surfaces, and potentially altering materials. But without a shockwave, the mechanical force is far less than what would be experienced within an atmosphere. The fireball itself is composed of extremely hot plasma, ionized particles moving at high speeds, and as it expands, it becomes thinner, less dense, until it blends into the surrounding vacuum, leaving no lasting structure, no cloud, no visible trace after a short period. From a distance, the explosion would appear as a brief flash of light, expanding and fading quickly, a small and temporary event against the vast darkness of space, easily missed unless one is observing at exactly the right moment. This kind of explosion highlights an important truth, that much of what we associate with explosive force is not just the energy itself, but how that energy interacts with its surroundings. And when those surroundings are removed, what remains is a more fundamental expression of energy, pure, radiant, and fleeting. As your thoughts continue to drift through this quiet emptiness, imagine now that this same burst of energy occurs not in open space, but upon a small, irregular body, a wandering rock or icy fragment moving through the solar system, where gravity is weak and structure is fragile, and where the explosion may not just disturb the surface, but reshape the object itself. The silent paths of asteroids and comets begin to take form in the distance. Now let your thoughts drift toward the quiet travelers of the solar system, the irregular bodies that move slowly along ancient paths, the rocky fragments we call asteroids, and the icy wanderers known as comets, objects that are small compared to planets, fragile in structure, and shaped more by their history than by internal forces. And here, a nuclear explosion does not simply leave a mark. It can change the object itself in more dramatic ways. Unlike planets, these bodies have very weak gravity, often so weak that a gentle push could send material drifting into space. And because of this, when a nuclear explosion occurs on or near such an object, the energy released interacts with a structure that is loosely held together, sometimes not even a solid mass, but a collection of rubble, fragments held together by gravity alone. At the moment of detonation, the fireball forms and expands as it would in vacuum, but now it is immediately interacting with the surface material, rock, dust, or ice, depending on the object, and because there is little gravity to hold this material in place, much of it is blasted outward at high speed, escaping the body entirely rather than falling back. On a rocky asteroid, the explosion can carve out a crater, but unlike on a planet, the edges may not remain intact. The structure can fracture, cracks spreading outward through the body, and in some cases, the entire asteroid may break apart, separating into multiple pieces that drift away from each other, slowly moving along new paths through space. If the asteroid is a rubble pile, loosely bound, the explosion may not create a clean crater at all. Instead, it can disperse the material, sending clusters of rock outward, reshaping the object into a cloud of fragments. Each piece continuing its journey independently, the original form lost, replaced by a scattered field of debris. On a comet, the effects become even more dynamic. Because of the presence of ice and volatile materials, when exposed to the intense heat of the explosion, these materials do not simply break, they vaporize rapidly, turning into expanding gas, creating a bright and fast-moving plume that pushes material outward even more effectively. This sudden release of gas can act like a jet, altering the motion of the comet itself, changing its rotation, slightly shifting its trajectory. Small changes on a cosmic scale, but meaningful over long periods. As the object continues its path around the sun, the plume from a comet explosion may resemble a miniature version of its natural tail, glowing faintly as it expands into space, carrying dust and gas away, forming a temporary cloud that slowly disperses, blending into the background of the solar system. Radiation from the explosion travels outward freely, as in open space, affecting any nearby objects, but the primary visible effect remains the physical transformation of the body, fragmentation, dispersal, and the creation of new debris. From a distance, such an event might appear as a brief flash followed by the gradual spreading of material, a cloud that grows and fades, marking the moment when a single object became many, when structure gave way to motion. Over time, these fragments continue along their paths. Some may remain loosely grouped, others drift apart completely, becoming new and independent bodies, each carrying a piece of the original, each shaped by that single moment of energy release. As this scattered cloud slowly fades into the vastness of space, allow your thoughts to move towards something more structured, more precise, human-made objects moving in orbit, where technology replaces natural material, and where the effects of radiation and energy become more delicate, more immediate. The quiet presence of satellites and spacecraft begins to emerge around distant worlds. Now let your thoughts drift gently toward the quiet paths that circle our world, where human-made objects move in steady motion. The delicate structures we call satellites, and the more complex machines known as spacecraft, each one carefully built, balanced, and sustained in the thin boundary between Earth and the vast openness beyond. And here, a nuclear explosion does not create roaring destruction, but something quieter, more subtle, and often more dangerous over time. In orbit, there is no atmosphere to carry a shockwave, no pressure front to physically strike these objects in the way we imagine on Earth. And yet the absence of air does not mean safety, because the primary force of a nuclear explosion in space is not the blast, but the radiation, the invisible flow of high-energy particles and electromagnetic waves that spread outward at incredible speed. At the moment of detonation, a bright flash expands into the vacuum, and within that flash is a surge of gamma rays, X-rays, and fast-moving charged particles. These pass through space almost unhindered, and when they encounter a satellite or spacecraft, they interact directly with its materials, penetrating outer layers, reaching sensitive electronics, and disrupting the delicate systems that keep it functioning. Electronic components are particularly vulnerable. Tiny circuits designed for precision can be overwhelmed by sudden bursts of energy. Signals can be scrambled, memory can be corrupted, and in some cases, systems may shut down completely, not because they were physically broken apart, but because the internal balance of electrical behavior was disturbed in an instant. One of the most significant effects in this environment is the electromagnetic pulse, often called EP, which in space behaves differently than on Earth. Without an atmosphere, the pulse spreads in a wider and more direct way, interacting with objects over a broad area, inducing currents in conductive materials, potentially damaging multiple systems at once. Unlike a single impact, these effects can persist. The radiation from the explosion can become trapped in planetary magnetic fields, especially around Earth. forming artificial radiation belts that linger, slowly degrading satellites over time, exposing them to levels of radiation far beyond what they were designed to withstand. The structure of a spacecraft itself may remain intact, its body unbroken, its orbit unchanged. Yet internally it may become silent, its sensors unresponsive, its communication lost, drifting through space as a quiet shell, still moving along its path, but no longer active. For astronauts, the situation becomes even more serious. Without the protection of a thick atmosphere, exposure to intense radiation can pose immediate risks, requiring shielding and careful positioning to reduce harm, making such events deeply significant for human presence in space. Debris also becomes a concern, not from the explosion itself, but from any damaged objects. Fragments of satellites or components may begin to drift, creating hazards for other spacecraft, each piece moving at high speed, capable of causing further damage upon impact. From a distant perspective, the explosion itself is brief, a flash that fades quickly, but the consequences ripple outward quietly, affecting systems, altering orbits indirectly, creating invisible zones of danger that persist long after the light has vanished. As your thoughts continue to drift through these quiet orbital paths, imagine the invisible forces at work, not just radiation, but energy interacting with fields and particles, shaping regions that cannot be seen, but can be felt by the machines that travel through them. And now gently allow your mind to focus on one of these forces more closely: the electromagnetic pulse itself, how it forms, how it moves, and how it behaves differently depending on where it is released, becoming a silent wave that reaches far beyond the moment of the explosion. Now let your thoughts settle into something quieter and more subtle, something that cannot be seen directly, yet travels farther than the eye can follow. The phenomenon is electromagnetic pulse, often called MP, a wave of energy that emerges instantly from a nuclear explosion, spreading outward like a silent signal through space and across worlds, shaping outcomes without leaving visible marks. At the moment of detonation, along with heat and radiation, there is a sudden release of electromagnetic energy, created as high-energy particles interact with surrounding materials and fields, and this energy forms a pulse, a rapid change in electric and magnetic fields that expands outward at the speed of light, touching everything in its path without resistance. On a planet like Earth, the atmosphere plays an important role. It interacts with the radiation, especially gamma rays, producing cascades of charged particles that amplify the electromagnetic effects. This creates a strong and widespread MP that can travel across large distances, affecting electrical systems far from the point of explosion, turning a localized event into a broad and interconnected disruption. In contrast, in open space or on worlds without atmospheres, the EP behaves in a more direct and less amplified way. There are fewer particles to interact with, fewer cascading effects, and so the pulse spreads outward more cleanly, affecting objects in its path, but without the large-scale amplification seen in atmospheric conditions. However, this does not mean the effect is weak. In space, where there is little shielding, sensitive systems are exposed directly. Satellites, spacecraft, and instruments can experience sudden surges in electrical currents. Circuits can overload, signals can be disrupted, and the precise timing systems that guide navigation and communication can be thrown into confusion. Planetary magnetic fields add another layer of complexity. On Earth, charged particles from a nuclear explosion can become trapped along magnetic field lines, forming artificial radiation belts, regions where energetic particles linger, circling the planet, slowly losing energy over time, but continuing to pose a risk to satellites that pass through these zones. On planets with strong magnetic fields, similar effects can occur. though shaped by the unique structure of each field, guiding particles into patterns that are not immediately visible, but deeply influential. While on planets without significant magnetic protection, these particles escape more freely into space, reducing long-term accumulation but increasing immediate spread. The MP itself is incredibly fast, moving outward at the speed of light, meaning its effects are felt almost instantly across great distances, far faster than any physical debris or thermal wave could travel, making it one of the earliest and most far-reaching consequences of a nuclear explosion. What makes EMP especially interesting is that it does not rely on direct contact. It does not need to strike or collide. It simply passes through, interacting with conductive materials, inducing currents, altering electrical states, and then continuing on, leaving behind systems that may appear unchanged on the outside but altered within. From a distant perspective, there is no visible sign of this pulse, no glowing wave or expanding ring, only the quiet knowledge that something has passed, something that has touched objects far beyond the visible flash, linking distant points through an invisible moment of energy. As your thoughts drift along this silent wave, imagine it moving across different worlds, shaped by their atmospheres, guided by their magnetic fields, interacting with everything it encounters. And now gently allow your mind to follow the energy further, beyond the immediate pulse, into the lingering presence of radiation itself, how it spreads, how it settles, and how its effects differ from one environment to another. Now let your thoughts drift into something even more subtle, something that lingers after the flash has faded, after the fireball has cooled, after the motion has slowed, the quiet presence of radiation, an invisible traveler that moves through space and across surfaces, shaping environments in ways that are not immediately seen, yet deeply real. At the moment of a nuclear explosion, radiation is released in several forms: gamma rays, neutrons, and charged particles, each carrying energy outward, each interacting with matter in different ways. And unlike heat or shockwaves, radiation does not require a medium to travel. It moves freely through vacuum, through thin atmospheres, and even into solid materials, passing through layers, depositing energy as it goes. On a planet with a dense atmosphere, such as Earth or Venus, much of this radiation is absorbed or scattered before it can travel far. The atmosphere acts like a shield, breaking down high-energy particles, spreading their energy across large volumes, reducing the intensity at any one point, yet also allowing secondary effects to form as particles interact with air molecules, creating cascades of additional radiation and ionization. In contrast, on airless worlds like the Moon or Mercury, radiation moves outward almost unimpeded. There's nothing to stop it, nothing to scatter it, and so it travels in straight paths, extending far into space while also striking the surface directly, altering materials at the microscopic level, changing atomic structures, leaving behind a subtle but lasting imprint. On Mars, where the atmosphere is thin, the behavior falls somewhere in between. Some radiation is absorbed, some escapes, and the result is a mixed pattern, localized effects on the surface, combined with partial spread through the air, yet still far less contained than on Earth. One important distinction is between immediate radiation and lingering contamination. The initial burst happens quickly, a sudden release of energy, but some radioactive materials may remain in the environment, depending on the composition of the device and the materials involved. On planets with atmospheres, these materials can attach to particles, drift with winds, and settle over time, spreading their influence across wider areas. On airless bodies, however, there is no wind, no rain, no atmospheric movement, and so any radioactive material that settles tends to remain where it lands, forming a localized zone of alteration, quiet and stable, changing only slowly over long periods. In gas giants like Jupiter and Saturn, radiation is absorbed into the vast atmospheres, interacting with gases, contributing to local heating, but quickly becoming diluted within the immense scale of the planet, its effects fading as they are spread across enormous volumes. Magnetic fields also influence the journey of radiation. Charged particles can become trapped, guided along invisible khututi, circling planets, forming belts that persist, slowly decaying, but continuing to interact with anything that passes through them, adding a layer of long-term influence beyond the initial event. Temperature, pressure, and composition all quietly shape how radiation behaves, how far it travels, how long it lingers, and how it interacts with matter, creating differences that are subtle but significant when viewed across different worlds. From a distance, radiation leaves no visible trace, no cloud, no motion, only the knowledge that energy has passed, that matter has been altered in ways too small to see, yet real and measurable. A quiet transformation following a moment of intense release. As your thoughts continue to drift through this invisible landscape, imagine the energy not just moving outward, but also shaping temperature itself, influencing how heat spreads, how fireballs expand, and how different environments respond to sudden changes in energy. And now gently allow your mind to focus on the warmth and brightness of the explosion once more, exploring how temperature behaves differently across the varied worlds we have visited. Now let your thoughts return gently to the warmth at the heart of every nuclear event, the intense heat that forms the fireball, a glowing sphere of energy that expands outward, carrying light and temperature into its surroundings. And yet, even this most fundamental aspect changes quietly from one world to another, shaped by atmosphere, pressure, and the ability of the environment to hold or release that heat. At the instant of detonation, temperatures rise to extreme levels, far beyond anything naturally found on planetary surfaces, creating a sphere of plasma, matter so hot that it no longer behaves as solid, liquid, or gas, but as a charged, luminous state. And this fireball begins to expand, driven by the pressure of its own heat. On a world like Earth, the atmosphere resists this expansion. Air is pushed outward, compressed into a shockwave, and the fireball grows while transferring heat into the surrounding gases, creating the familiar rising motion and the development of a cloud structure. But this process also slows the cooling because the atmosphere traps heat, holding it near the surface for longer periods. In contrast, in open space or on airless bodies such as the moon, the fireball expands without resistance. There is nothing to contain it, nothing to slow its growth, and so it spreads rapidly, thinning as it grows, losing temperature quickly as its energy is distributed over a larger volume, causing it to fade much faster than it would in an atmosphere. On Mars, with its thin atmosphere, the behavior lies between these extremes. There is some resistance, enough to slightly shape the fireball and allow limited heat transfer to the air, but not enough to trap the energy for long. The fireball expands and cools more quickly than on Earth, yet not as instantly as in a vacuum, creating a brief and subtle thermal interaction with the environment. On Venus, the situation becomes very different. The dense atmosphere resists expansion strongly, compressing the fireball, slowing its growth, and allowing it to retain heat for a longer time. The surrounding gases absorb this heat and distribute it slowly, creating a more prolonged thermal effect, where the environment itself remains heated beyond the initial moment of the explosion. In the gas giants like Jupiter and Saturn, the fireball interacts directly with thick layers of gas, transferring heat into the atmosphere. But the immense volume of these planets quickly dilutes the energy. The heat spreads into the surrounding layers, becoming part of the larger thermal system rather than remaining concentrated. Temperature differences in the environment also influence how materials respond. On icy worlds such as Europa, the sudden heat creates rapid melting and vaporization, while on hotter worlds like Venus, The surrounding material is already near extreme conditions, and additional heat pushes it further, altering its flow and behavior in subtle ways. The fireball itself is always temporary. Its brightness and heat are intense but short-lived, fading as energy spreads outward. Yet the way it fades, the speed of cooling, the distance it reaches, all depend on the environment, making each explosion unique in its thermal signature. Even light behaves differently. In dense atmospheres, it can scatter, creating a glowing effect that lingers, while in vacuum it travels cleanly, a sharp flash that fades quickly without diffusion. As your thoughts drift through these layers of warmth and fading light, imagine how this heat interacts not only with matter, but with motion itself, how it drives expansion, how it creates waves, and how those waves depend entirely on the presence of a medium. And now gently allow your mind to follow this idea further into the physics of shockwaves, how they form, how they travel, and why they exist only where something is there to carry them. Now let your thoughts settle into the quiet movement of pressure itself, the invisible push that travels through matter, shaping what we call a shockwave, a sudden and powerful change in pressure that moves outward from an explosion. And yet, this familiar force depends entirely on something very simple. There must be a medium, something to carry it, something to compress and release. A shockwave forms when energy is released so quickly that the surrounding material cannot move out of the way smoothly. Instead, it is forced into a tight, moving boundary, a front where pressure, temperature, and density all change suddenly. And this front travels outward, carrying force across distance, but without a medium, without particles to compress. This process cannot occur. On Earth, the atmosphere provides a dense and continuous medium. Air molecules are pushed together, forming a strong and fast-moving shockwave. This is what creates the familiar blast effects, breaking structures, moving objects, and shaping the rising cloud that follows the explosion. On Mars, where the atmosphere is thin, the shockwave still forms, but it is weaker. The lower density means fewer particles to compress, and so the wave spreads out and loses strength more quickly, traveling shorter distances with less force, becoming a softer echo of what we see on Earth. On Venus, the opposite occurs. The atmosphere is extremely dense, and this allows the shockwave to carry more energy, to move through a thicker medium, maintaining its strength over longer distances. The pressure changes are more sustained, the movement more powerful, yet also more controlled, shaped by the resistance of the heavy air. On airless bodies like the Moon and Mercury, there is no atmosphere, no medium in which a shockwave can form, and so the concept of a blast wave disappears. There is no moving wall of pressure, no expanding ring of force, only the direct transfer of energy into the surface and the outward motion of debris. In gas giants such as Jupiter and Saturn, the shockwave exists within a vast and deep atmosphere. But here, the scale changes everything. The wave moves through layers of gas, interacting with currents, pressure gradients, and temperature differences, becoming part of a complex system of motion rather than a simple expanding front. Even within these planets, the depth matters. In upper layers, the shockwave may spread more freely, while in deeper regions where pressure is immense, the wave becomes more compressed, its energy absorbed more quickly, its motion slowed by the density of the medium. Temperature also influences shockwaves. Warmer gases expand more easily, altering how the wave moves, while colder environments may resist expansion differently, creating variations in how pressure is transmitted. On icy worlds, where there is little or no atmosphere, shockwaves do not travel through air, but energy can still move through the solid surface itself, creating seismic waves, vibrations that pass through ice or rock, spreading outward beneath the surface, adding another layer of motion that is not visible, but deeply important. This reveals something gentle yet profound. that a shockwave is not a thing on its own, but a relationship between energy and matter. It exists only where there is something to carry it, something to respond. And without that response, the wave cannot form. As your thoughts drift along these invisible paths of pressure, imagine how each world shapes the movement differently, how the same burst of energy creates entirely different patterns depending on what surrounds it. And now gently allow your mind to move beyond the immediate blast, into the secondary effects, the subtle changes that follow, the dust, the clouds, the disturbances that linger after the main event has faded into silence. Now let your thoughts slow even further, moving past the instant of brightness and pressure, into what remains afterward, the quieter effects that unfold gently over time, the dust that rises and settles, the clouds that drift and fade, the subtle disturbances that continue long after the main energy has dispersed, shaping each world in small but meaningful ways. On a planet like Earth, these secondary effects can become vast and complex. The explosion lifts dust, debris, and particles high into the atmosphere, where they are carried by winds, forming clouds that spread across regions, sometimes altering light, temperature, and even weather patterns for a time. The environment responding not just to the initial force, but to the materials placed into motion. On Mars, the fine dust that covers the surface is easily disturbed, and when lifted by an explosion, it can create a wide, spreading cloud that moves slowly through the thin atmosphere. Influenced by gentle winds, this cloud may persist for a while, drifting across the landscape, softening visibility, blending into the natural dust cycles that already define the planet. On airless bodies like the Moon, there are no clouds in the traditional sense, no air to carry particles, yet the motion still occurs. Debris rises and falls in graceful arcs, settling slowly back onto the surface, forming a new layer of fine material, altering the texture of the ground in a quiet and lasting way. On icy worlds such as Europa, the secondary effects take the form of plumes and frost. Vaporized ice rises and then cools, condensing into tiny crystals that drift back down, covering the surface in a fresh, bright layer, a gentle return to stillness after a moment of intensity. On Venus, the dense atmosphere carries particles differently. The heavy air slows their motion, allowing them to remain suspended for longer periods, forming thick and slowly moving clouds, the disturbance blending into the already complex and layered cloud systems of the planet. In gas giants like Jupiter, secondary effects are seen as changes in cloud patterns, temporary openings, darker or lighter regions, and subtle shifts in motion, all gradually stretched and reshaped by powerful winds until they are no longer distinguishable from the surrounding atmosphere. On small bodies like asteroids and comets, the secondary effect is often the dispersion itself. Material does not settle back easily. It drifts away, forming temporary clouds of debris that slowly spread into space, becoming part of the broader environment, rather than returning to a single location. Temperature differences created by the explosion can also lead to gentle flows, warm regions rising, cooler regions sinking, creating slow movements in atmospheres or subsurface layers, subtle currents that continue after the main event has ended. Even light can be affected. Particles suspended in atmospheres can scatter sunlight, creating temporary changes in brightness or color, altering the appearance of the sky or surface when viewed from a distance. These secondary effects are quieter than the explosion itself, but they last longer, unfolding slowly, shaping the environment in ways that are not immediate but persistent, leaving behind traces that may remain visible long after the initial flash has disappeared. As your thoughts continue to drift through these gentle movements, imagine how these small changes can accumulate over time, how repeated events or larger disturbances might begin to influence entire environments, And now softly allow your mind to move toward the longer view, the lasting impact on worlds themselves, how surfaces change, how atmospheres respond, and how the memory of energy becomes part of the planet's story. Now let your thoughts settle into a slower rhythm, moving beyond the immediate aftermath, beyond dust and fading light, into the long memory of worlds, the way a planet or moon quietly holds on to what has happened, how energy leaves traces that last far longer than the moment itself, becoming part of the ongoing story, written across surfaces and skies. On a solid world like Earth, long-term effects are shaped not only by the explosion, but by the living systems that follow. Atmosphere, water, and biological processes begin to respond. Particles settle, materials are redistributed, and over time the environment slowly absorbs and transforms the changes, sometimes erasing them, sometimes preserving them in subtle ways. On the moon, where there is no atmosphere and no active erosion, the memory is far more permanent. A crater formed by an explosion may remain almost unchanged for millions of years. Its edges sharp, its structure clear, a quiet mark that endures, slowly collecting dust from micrometeorites, but otherwise preserved in stillness. On Mars, the story lies between these extremes. The thin atmosphere allows some erosion. Winds slowly reshape the surface. Dust fills in depressions, softening the features of a crater over long periods, blending it into the surrounding landscape, yet still leaving a recognizable imprint of what once occurred. On Venus, the environment itself works more actively. The high temperatures and pressures gradually alter the surface, melting, softening, and reshaping features, so that over time, the clear marks of an explosion may fade, becoming less distinct, absorbed into the planet's constantly evolving surface. In the gas giants such as Jupiter and Saturn, there is no lasting mark at all in the traditional sense. The atmosphere is always in motion, clouds shift, storms form and dissipate, and any disturbance created by an explosion becomes part of this endless flow, its identity lost within the larger patterns of the planet. On icy moons like Europa, the long-term effects may include fractures that slowly refreeze, layers of ice that record the disturbance beneath new surfaces, subtle lines and patterns that hint at past events, preserved in frozen time. On small bodies such as asteroids, the long-term impact may be the most dramatic. Not just a mark, but a transformation. Fragmentation, reshaping, the creation of entirely new objects that continue to move through space, carrying the memory of the event within their altered paths. Radiation can also leave a lasting signature, changing the structure of materials, altering isotopes, creating subtle differences that can be detected long after the visible effects have faded. A quiet record written at the atomic level. Climate and atmospheric systems, where present, may respond over time, small changes accumulating, particles influencing light and temperature. Though for a single explosion, these effects remain limited compared to the scale of a planet, they still contribute to the overall balance in subtle ways. What becomes clear in this quiet reflection is that each world remembers differently. Some preserve every detail, some slowly reshape the past, and some absorb it completely, leaving no trace at all. And in this way, the same event becomes many different stories, written in different languages of rock, ice, gas, and time. As your thoughts drift through these lasting impressions, imagine now the human perspective, the fragile presence of exploration, the machines and people who might encounter such environments, and how these forces, radiation, heat, and change, would shape the future of exploration and the delicate effort to exist beyond Earth. Now let your thoughts return gently to something more familiar, the human presence that slowly extends beyond Earth, fragile and carefully sustained, moving through space in small vessels and orbiting machines, reaching toward other worlds with curiosity and precision. And within this delicate expansion, the idea of a nuclear explosion becomes not only a scientific question, but a matter of safety, planning, and quiet caution. For astronauts traveling beyond Earth, the environment is already challenging. Space offers no natural protection from radiation, no atmosphere to soften extremes, and every system must be designed to shield, regulate, and sustain life. And in such conditions, a sudden burst of nuclear energy introduces risks that are immediate and difficult to avoid. Radiation becomes the primary concern. High-energy particles released in an explosion can pass through spacecraft walls, interacting with human tissue, increasing exposure levels quickly and without proper shielding. This can pose serious health risks, making distance and positioning essential factors in reducing harm. Inside a spacecraft, electronics are just as vulnerable. Navigation systems, communication arrays, life support controls all rely on stable electrical behavior, and a strong burst of electromagnetic energy can disrupt these systems, causing temporary failures or permanent damage, turning a functioning vessel into a silent object drifting through space. On planetary surfaces, the risks vary depending on the environment. On the Moon or Mars, where future missions aim to establish longer presence, a nuclear event would not produce the same widespread atmospheric effects as on Earth, but the direct radiation and surface disturbance would still pose serious localized dangers. Habitats, whether temporary or permanent, would need to be shielded carefully, using materials or natural features, such as underground placement or thick regolith covering to reduce exposure. And even then, planning would involve maintaining safe distances from any potential sources of such energy. On worlds with dense atmospheres like Venus, human presence is already extremely limited due to environmental extremes, but if technology ever allows exploration, the behavior of energy within such dense conditions would require careful study to understand how pressure and heat interact with protective systems. In orbit around Earth or other planets, satellites and stations remain exposed, and the creation of artificial radiation belts following an explosion could make certain orbital paths hazardous for extended periods, affecting communication networks, navigation systems, and scientific instruments. Even small fragments created by damaged objects become a concern, traveling at high speeds. These pieces can pose collision risks, turning a localized event into a wider challenge for maintaining safe orbital environments. From a human perspective, the key idea is not just the power of the explosion, but the vulnerability of the systems that support life and exploration, the need to anticipate, to protect, and to design with awareness of these forces. And yet, within this understanding, there is also curiosity, the desire to learn, to explore, to use knowledge not for destruction, but for insight, guiding how technology is developed and how space is approached with care and respect. As your thoughts continue to drift, imagine not only the risks, but the questions that arise. Could such energy ever be used in controlled ways? Could it serve scientific purposes, or even shape environments intentionally? And now gently allow your mind to explore these ideas, the careful balance between possibility and responsibility, between curiosity and caution. Now let your thoughts drift into a more reflective space, where the same immense energy is no longer imagined only as a sudden event, but as something that has been considered, studied, and questioned, not for destruction, but for possibility, for understanding, and for the careful exploration of what could be done and what should remain only an idea. Throughout history, scientists and engineers have sometimes wondered whether nuclear energy, with all its intensity, could be used in controlled ways beyond Earth, not as a weapon, but as a tool, a source of power capable of shaping environments or enabling exploration in extreme conditions. Ideas that exist quietly at the edge of science and imagination. One such idea has been the concept of altering small celestial bodies such as asteroids, using energy to change their paths, not by destroying them completely, but by gently shifting their motion, a small change in direction that over long periods could prevent potential impacts with planets. A form of planetary protection that relies on careful calculation rather than force. Another area of thought has involved using nuclear energy as a propulsion method in space travel, where controlled bursts could provide momentum, allowing spacecraft to move more efficiently across vast distances. An idea that has been explored in theory, where the energy is harnessed in a directed and managed way, rather than released freely. There have also been speculative ideas about influencing environments on other worlds, sometimes called planetary engineering, where energy might be used to trigger changes, perhaps releasing gases trapped in ice, or altering local conditions, not as a sudden transformation, but as a gradual process guided by repeated, controlled inputs. Yet, these ideas remain deeply complex and often uncertain, because the environments we have explored, from the thin air of Mars to the dense clouds of Venus, respond in ways that are not always predictable. And the scale of these worlds is so vast that even immense energy becomes small when compared to planetary systems. There's also the question of unintended effects, how a change in one part of a system might lead to shifts elsewhere, how delicate balances could be disturbed, and how difficult it can be to fully understand the long-term consequences of even a single action. Because of this, such ideas are approached with caution, studied in theory, modeled through simulations, and discussed within scientific communities, where the focus is not only on what is possible, but on what is responsible, what aligns with the careful exploration of space rather than its disruption. What becomes clear is that nuclear energy, while powerful, is not a simple tool. It is something that interacts deeply with its environment, shaped by conditions, influenced by scale, and carrying consequences that extend beyond the moment of its release. And so, as your thoughts drift through these quiet considerations, there is a sense of balance between curiosity and restraint, between the desire to explore and the need to preserve, a recognition that understanding the universe does not always require changing it. Now, as this reflective space settles, allow your mind to move gently toward another important aspect, not of physics, but of agreement, the shared understanding among those who explore space, the rules and principles that guide how such powerful forces are treated beyond Earth, shaping not just what can be done, but what is chosen to be done. Now let your thoughts settle into something quieter still, not the movement of energy or matter, but the gentle framework that surrounds human activity in space, the agreements that exist between nations, the understanding that the space beyond Earth is not owned in the same way as land below, but shared, open, and approached with care. As exploration expanded during the 20th century, there was a growing awareness that the power carried into space could shape not only discovery, but also risk. And so nations began to create agreements that would guide behavior beyond Earth, not to limit curiosity, but to prevent harm, to keep space a place for peaceful exploration rather than conflict. One of the most important of these is the Outer Space Treaty, an agreement that sets the foundation for how space is used, stating that celestial bodies, such as the Moon and other planets, are to be used for peaceful purposes, and that nuclear weapons or other weapons of mass destruction are not to be placed in orbit or stationed on these bodies. This does not mean that nuclear energy itself is entirely forbidden in space, because controlled and peaceful uses, such as power sources for spacecraft, have been part of exploration. But it does mean that the uncontrolled use of nuclear explosions as weapons is restricted, shaped by a shared understanding of their potential consequences. There are also agreements that focus on testing, such as the Partial Test Ban Treaty, which limits nuclear explosions in the atmosphere, underwater, and in space, reflecting a concern not only for immediate effects, but for the broader impact on environments and on global safety. These agreements are not just rules. They are expressions of a collective choice, a recognition that while technology allows for powerful actions, not all actions need to be taken, and that the exploration of space carries a responsibility to protect both the environments we visit and the systems that support life and communication. Even in orbit around Earth, these principles influence how systems are designed, how risks are managed, and how nations communicate, because the space around our planet is shared by many, filled with satellites, research instruments, and pathways that must remain safe and stable. There is also a quieter ethical layer, the idea that celestial bodies, untouched for billions of years, are not just locations but records of cosmic history, and that altering them unnecessarily could erase information that has been preserved across time. A kind of respect for the natural state of the universe. Of course, agreements evolve. They are discussed, interpreted, and sometimes challenged, but they remain an important part of how humanity approaches the vastness beyond Earth, not only with curiosity, but with caution and cooperation. As your thoughts drift through these shared understandings, imagine space not just as a physical place, but as a collective effort, a network of knowledge, responsibility, and quiet agreement, guiding how powerful forces are treated among the stars. And now, gently, allow your mind to move toward the final reflections, where all these ideas come together. The physics, the environments, the human perspective, and the quiet rules that shape them, forming a complete picture of how a single burst of energy can mean so many different things across the universe. Now let your thoughts drift into a quieter reflection, where imagination meets reality, where the images often seen in stories and films gently dissolve into the deeper and calmer understanding we have built together. Because when we think about nuclear explosions across planets, it is easy to picture dramatic scenes, massive waves, planets breaking apart, or fire spreading endlessly. Yet the true behavior is more subtle, more dependent on conditions, more shaped by quiet physical rules. In many imagined scenarios, explosions in space are shown as loud, expanding blasts, pushing objects away with force, creating clouds and waves similar to those on Earth. But as we have seen, without an atmosphere, these familiar effects do not exist. There is no sound, no traditional shockwave, only light and radiation moving outward in silence, a brief and fading event rather than a sustained spectacle. Another common idea is that a nuclear explosion could easily destroy a planet, breaking it apart or causing massive global change. Yet when we consider the scale of planets like Jupiter or even rocky worlds such as Mars, we begin to see how small even powerful human-made energy is compared to planetary mass and gravitational binding. A single explosion, or even many, would remain localized, unable to alter an entire world in any dramatic way. On the Moon, the image of a massive visible change might seem more reasonable, yet even there, the result would be just another crater among many, a small addition to a surface already shaped by countless impacts over billions of years, blending into the quiet history of that world. Films often show fire spreading across surfaces or through space. Yet fire as we know it requires oxygen, and without an atmosphere, combustion cannot continue. What we see instead is a brief flash of heated material, fading quickly, not a sustained burning process. There is also the idea of chain reactions across environments, where one explosion triggers another, spreading across a planet. But in reality, most planetary materials do not support such reactions. The energy dissipates, interacts locally, and then fades, rather than propagating endlessly. Even radiation is often imagined as a visible cloud, something that moves like smoke, yet in reality, much of it is invisible, traveling quietly, interacting at a microscopic level, leaving changes that are real, but not easily seen. What becomes clear in this calm reflection is that the universe does not exaggerate. It follows consistent principles. Energy behaves according to conditions, shaped by atmosphere, gravity, and composition, and each world responds in its own way, without drama, without intention, simply following the laws that govern it. And in this understanding, there is something peaceful, the realization that even powerful events fit into a larger balance, that the scale of the universe is vast, and that individual moments, no matter how intense, become part of a broader, steady system. As your thoughts continue to slow, allow all of these ideas to come together, the differences between worlds, the movement of energy, the quiet effects that follow, forming a complete picture. And now gently prepare to step into the final part, where everything we have explored will settle into one calm and unified understanding. Now let your thoughts come to rest in a calm and steady place, where everything we have explored begins to settle into a single, continuous understanding. A gentle synthesis of energy, environment, and scale, where the same nuclear event, simple in its origin, becomes endlessly varied in its expression across different worlds. At its core, a nuclear explosion is always the same, a sudden release of immense energy from the smallest structures of matter, a brief transformation where mass becomes heat, light, and motion. Yet, what follows is never the same twice, because the universe does not respond uniformly. Each environment shapes the outcome in its own quiet way. On airless worlds like the Moon and Mercury, the event is silent and clean, a flash, an expanding sphere, and a scattering of material that rises and falls without resistance, leaving behind a sharp and lasting mark, a memory preserved in stillness for ages. On Mars, the presence of a thin atmosphere softens and shapes the event, allowing faint waves of pressure and drifting dust, creating a balance between motion and silence, between change and preservation. On Venus, the dense atmosphere holds the energy close, compressing it, slowing its escape, turning the explosion into a more contained and prolonged interaction, where heat lingers and pressure carries the effects farther through heavy air. In the vast atmospheres of Jupiter and Saturn, the explosion becomes almost insignificant in scale, absorbed into layers of gas, leaving only temporary disturbances, patterns that stretch and fade within the endless motion of clouds. On the cold and distant Uranus and Neptune, the energy sinks quietly into dense and frigid atmospheres, creating subtle and short-lived changes, quickly blending into the vastness of these distant giants. On icy moons like Europa and Enceladus, the explosion awakens frozen material, creating plumes of vapor and light, brief fountains that rise and fall, leaving behind delicate layers of new ice. On the restless surface of Io, the energy meets an already active world, blending with volcanic processes, becoming part of an ongoing cycle of heat and motion. In open space, the explosion is reduced to its most fundamental form, a silent burst of radiation and light, expanding freely, fading quickly, leaving no trace beyond the brief passage of energy. On small bodies like asteroids and comets, the effects can be more transformative, reshaping or dispersing the object, turning one body into many, altering paths that continue through time. And for human presence, in orbit or on distant surfaces, the same event becomes a matter of vulnerability and care, where radiation, electromagnetic effects, and debris shape the way exploration must be approached with awareness and protection. Across all these environments, one quiet truth remains: the explosion itself is only the beginning. The real story is how each world receives it, how energy interacts with matter, how conditions guide outcomes, and how scale defines significance. In the end, even the most powerful human-made energy is small compared to the vast systems of planets and space. It creates moments, not transformations. It leaves marks, not global change. And those marks, whether preserved, reshaped, or erased, become part of the ongoing story of the universe. As your thoughts settle into this final understanding, there is a calm sense of balance, the realization that the universe is both powerful and steady, that even intense events fit within a larger order, and that by understanding these interactions, we come a little closer to seeing the quiet harmony that connects all worlds. And now, gently, as the journey comes to rest, allow everything to fade into stillness, like a distant flash that has already softened into memory, leaving behind only a quiet sense of wonder.